the structure of this topic is not very different than what you just did. You still have triple integrals. What's changing? Everything else. Yeah, I mean, that's a simple way to put it, but instead you have these relationships that will allow you to convert. But what's the point? And I am asking this in a serious way. What's the point of a triple integral in cylindrical or spherical coordinates? Like, why would you ever need to do, if you assume, that if you are okay with the fact that triple integrals are useful for something, why would you need to do them in cylindrical or spherical coordinates? Say what? Some structure, you think it might make some things more easy? Yeah. That's a way of saying it. The more specific thing would be to say that the boundaries of your shape aren't always defined in Cartesian coordinates. You might have a three-dimensional shape that has a boundary that has some sort of weird rotation, that is some weird rotational solid. So cylindrical coordinates might be useful. Spherical coordinates are useful for certain shapes. So you might have boundaries that are better described by cylindrical or spherical coordinates. Do you already believe this is true for Cartesian and polar? Are there some equations that are there some double integrals and triple integrals that are easier to do in polar than they are in Cartesian? Yeah, absolutely. Is vice versa true? Are there some that are much, much easier to do in Cartesian than polar? Sure. If you see a straight line, you think to yourself, or a plane, you think to yourself, Cartesian. If you see a nice clover shape, you might think to yourself, polar. Are there other corollaries into the world of cylindrical and spherical coordinates? Absolutely. There's nothing very new. The definitions here are, you've seen these conversions before between Cartesian and cylindrical coordinates. And you see this triple integral right here, which looks visually terrible. All of it comes down to algebra. All of it comes down to algebra. I don't really like this topic too much because I like to graph things by hand, and we don't really have enough time to get into the software packages you would need in order to graph these with a computer. Is it hard enough to graph things in 3 dimensions that are defined in Cartesian and polar coordinates? Yes. So what do you think happens when you start defining things in spherical and cylindrical coordinates? It gets more harder, yes, more harder, right. This is the kind of shape that you would be integrating together. You'd have these, remember how we had polar rectangles? They look like bent rectangles. Do you remember those, polar rectangles? This right here is a spherical wedge. Great. You just have a lot of notation. This is notation heavy. This is notation heavy. I don't really like slogging through all the algebra, mainly because doing this equation right here, for example, this is evaluate this where B is the unit ball. You can convert this to, what do you think you convert that to, spherical or cylindrical? Spherical, actually. You go to spherical, and it actually falls out quite nicely. If it doesn't fall out quite nicely, you end up wading through tons and tons and tons of Greek letters. Do I like doing that? Not really. Since this class is ending pretty soon, and I've never really liked doing this topic, I don't feel as though it's super useful to you. I want you to be aware that, can you do triple integrals in cylindrical and spherical coordinates? Nod and say yes. Do you have to in this class right now? No, we're skipping it. Yay! Okay. 15.9 talks about how you can change around variables with multiple integrals. It's a lot of fun. It has to do with essentially how the chain rule plays out. And there are some rather powerful deep analyses that we can do with this method. But I really, really, really want to get to things that I think are more important for your future math career. Mainly because how many of you, for example, how many of you have dealt with deep matrix work before? Have you ever done huge inverses with 3x3 matrices? Not really. Remember how we've covered some topics where we've had to go back and relearn some things that that are between BC and multi, or that you haven't seen in a long time? In order to get really deep into change of variables, we would have to go back really far, and I want to use our time a little bit more effectively towards other topics. I also want to change gears a little bit away from algebra. So guess what we get to jump to? 16.1. Are you excited? Okay, so what do you see right there?
Canada.
I see Canada. Yeah, I see Canada. I see ocean. Ocean. What could this be modeling right here? Ocean current. At any given point, what does the arrow represent? The direction the current is going in at that specific point.
And it looks like magnitude as well.
It also, I mean, yeah, I know. I think these arrows are different lengths. You're right. It's hard to tell, right? It's hard to tell the tails, but the longer the arrow is, what does the longer arrow mean? Faster the current, the stronger the current. So this is a model of current. So here's the important definition. Let D be a set in R2. So we're in 2 dimensions. We like 2 dimensions, right? A vector field on R2 is a function f that assigns each point xy in D to a 2-dimensional vector xy. You actually have seen these before. What were they called when you had them in A, B, and BC calc? Slope fields. These are, so these, the way you saw these before, these were slope fields. But we're not in 2D calculus anymore. So what are we in? Multivariable calculus. So we get to extend this to 3 dimensions. So what's the only thing that's changed here? Has any new structure been added in? No. It's the same definition, just in 3 dimensions. That's it. Every point in 3 space gets an associated directional vector. That's it. That's all that's going on here. A vector field on R2 is defined by f of xy is equal to negative yi plus xj. Describe f by sketching some of the vectors as in figure 3. So you know what figure 3 looks like. So let's just sketch this. What does this mean? What is vector I? What is I? It is a unit vector, but it's the x direction, right? What's j? The y direction. Okay, so essentially what they want you to do here is sketch the slope field. Sketch the slope field right here. So how do you propose we go about sketching the slope field? First, recognize how many dimensions is it in? 2 dimensions. It's in 2 dimensions, so we're graphing this on a plane. At 0, 0, what does the vector become? At 0, 0, the vector becomes 0, 0. So you have a dot right there. It doesn't go anywhere. What about at the point 1, 0, when x is 1 and y is, when x is 1 and y is 0, what does it become? 0, comma what? 1. It becomes 0, 1. So what does the vector 0, 1 look like? So it's at this point, and where does it go? Straight up 1. What about at the point 2, 0? Straight up what? 2. So this one starts here and goes up 2. Let's do a few more. What does negative 1, 0 look like? 0. Negative 1? It is negative. So it goes here and then it goes down. What about negative 2, 0? 0, negative 2. So yes, that was a great suggestion, Nate. There's a few. Now, how many of these could we potentially draw if we wanted to? We could zoom in as much as we possibly wanted to. So you kind of have to use your intuition to figure out which ones you want to actually plot. So if we've plotted these 4, actually these 5, which 4 other ones do you think might be good to plot if we were to draw a helpful picture? Yeah. So how about 0, 1? What does that come out to? What was our function again? You can't really see it. Negative 1, 0, like this. So which way? Where's that point? It's right here. In which way is it going to point? Left. It's going to point left. Wow, this is not going to be an appropriate picture, apparently. What is 0, 2 going to be? Yeah, you got it. You'll figure it out eventually. Yeah, what's it going to come out to be? 0, 2. What does 0, 2 come out to be? Negative 2, comma, 0. So we plot it up here, 0, 2. So which way is it going? Well, hold on. We'll see. Let's pick one. Yeah. You want to like 1, 1? 1, 1 is a good one to test. So what's that going to come out to be? Negative 1, 1. So what does that mean? We're going to go to the left. We're at 1, 1 here. It means we're going to go left 1 and up 1. So it actually goes like that. So it actually goes up. And so is it continuing in that swirl fashion right there? Absolutely. So if you were to actually dot in just about every one you could on a circle, what would you potentially see? You would see an actual circle. Yeah, you would see all these essentially tangent lines coming off the circle, which is pretty interesting. So let's try. So it says sketch the vector field on R3 given by f of xyz is equal to zk. So graph that for me. Don't go wild, because kind of like when you graph any 3-dimensional structure, if you the more lines you draw, what happens to your picture? Ew. Yeah, ew. That's right. Ew. So what's nice about this one is that it's really easy to figure out what each magnitude and which direction each vector is supposed to go in, but because of the consistency, kind of breaks the perspective a little bit. I like that you picked just axial points. So the magnitude of each of these is going to be independent of their x and y coordinates. It's totally dependent on its z coordinate, right? And it's going up. And then what would happen as we go below the xy plane? What happens? They start pointing straight down. Good picture. I like. Jay, you want to tell me what it's supposed to be? So it's the partial with respect to x. 2xy, comma x squared
minus
3y squared. Exactly. So in this case, how many dimensions are we working in? Only 2 dimensions here. We're really only working on 2. This would be very awful to try to do in 3 dimensions by hand. So we're doing this in 2 dimensions right here. So we have... Anybody have Math League competitions? No, Math League, the talent search, right? Was it
It's the Vermont State Math Coalition Talent Search.
Anybody do a talent search during capstone season? You'll go get it?
Me after school.
No, I will send you separately.
Okay.
You send me on, send mine.
I have yours.
You have mine. How
I
will change
got-
the answer?
No, you're not changing the answer.
Wow. It's an aggressive mathematician right there.
It's nine.
I'm not changing the answer. It's fine. It's okay.
That's plus nine.
No, they're gonna want the work.
Yeah.
James,
I got change it on one.
Yeah, I resend it with the
you what?
I resend it with
You're gonna send
yeah,
it electronically?
separately.
No problem. Thank you very much.
No
Sorry.
problem, no problem. So 1, 1. If we plug in 1, 1, Nell, what's the vector become that correlates to? 2 comma 2 comma negative 2. So down 2. So over 2 and down 2. So how does that look right there? Does that look okay? Graph me 9 more points. Graph me 9 more points. Yeah, 9 more. Oh,
Nine.
Nine? Why nine?
it's kind of arbitrary.
It's a big arbitrary
Oh, if you can't see it, sorry. It really doesn't like this color. Hold on. Should come back.
That made a big difference.
Well, wouldn't be visual. Well, I guess the moral of the story is don't. So you've been doing this right here. So we've been doing this. I always thought of as you're scanning, you're adding that slice to this slice, you're slicing, lots of slicing. It's very hard to say that word fast. But you're scanning from left to right. What have we added into this? We've added in multiple dimensions, correct? We've done double integrals where we've had 2 bounds and a height. We've even had 3 bounds where we've defined a value for each point inside a 3 space, and we found the additive sum of all of those things. What's been the commonality about all of this scanning that I'm describing? It always goes, what kind of direction is this? Generally goes left to right. When I think of the scanning, I know I'm having you reach inside my head and pull out what I'm thinking of, but I always think of it as we're scanning from left to right. What kind of shape is this right here? A line. It's a straight line. We've always integrated across what? We have integrated across what? across lines. We've integrated across lines. We've integrated from like 0 to 1 on the x-axis. We've integrated from 0 to 7 on the y-axis. We've integrated with certain bounds, but it's always been in straight lines. Do you have to integrate across straight lines? Are you limited to straight lines? No, you're not. So what does that simplify to? 2 plus cosine squared t sine t times 1 dt. Now getting back to what Nate was pointing out, we need to have limits, right? We need to have limits. So what are we going from? Time equals 0 to time equals pi right over there. Kind of mirrors it nicely. No, yeah, if you had your calculator, you would use it, but what would you do? It's a u sub, yeah. It's a u sub problem right here. It's nice and straightforward. That's a u sub. It follows nicely. U is going to be equal to what? That's just cosine t, right? U is equal to cosine t. From what to what? T equals to 0, I think. 0 to what? 1. Yeah. Is 0 to 1 going to be the most common one you can make? Yeah. You can use any parametrization you want. Ones that start at 0 and end at time 1 are the ones that are probably going to be the easiest to evaluate. So you end up with 2 times the integral from 0 to 1 of t times the integral of 1 plus 4t squared. So what do you end up with? 2 times the integral from 1 to 2 of. Final answer to this question. 2 plus. Right here defines it as a type 1 region. What could you do? You could turn your head sideways. You could turn your head sideways, and what you're looking to do, Tony, is you're looking to do this. The integral of the same thing, cosine t squared, but instead of dt dx, what are you doing? dx dt. dx dt. So what does that get bounded by? What's the upper bound for x going to be? T and 0. And what's t going to be bounded by? 0 and 1. Can you integrate it now? Can you integrate it now? Yeah. Yeah, you do, but you're doing x first. Now you do x first. What does this become, everybody? 0 to 1 of what? T cosine t squared dt. And now can you finish it?